I have a 5.20 kilogram box. I lift it 1.55 meters into the air, and then I take that box after I've lifted it 1.55 meters vertically, up and down, then I take it and move it 9.70 meters horizontally. So I'm going to demonstrate that for you now. So here's my 5.20 kilogram box from Macy's. Okay, so I've lifted it about 1.55 meters into the air, and now I need to take it horizontally 9.7 meters. So the question I have, determine the work done by the person during the vertical lifting phase, and then also determine the work done by the person during the horizontal carrying phase. In that question, you might be surprised by the answer. So now to explain all this and how much work exactly that I did to answer both those two questions, I'm going to go ahead and send it to my good friend Eytan. And Eytan, who's waiting for us in the classroom to show us just how to do the problem. And tell me, Eytan, how much work did I just do? Yeah, that's right. Hi, Eytan. We're here in the classroom here, and I just wanted to thank you for showing us exactly what is going on in the problem so we have a good idea of the visual of what's going on there. Now I'm going to explain it using the formula work equals force times distance times cosine theta. So first of all, what do we know here? The distance is 1.55 meters. All right? Now we're on to force. So which force do you think we would use? Well, because it's vertical, up and down, that tells us that it's a force that's going up and down. And what comes to your mind? Force gravity. So force gravity is the force we're going to use. And in order to solve for force gravity, we need to do mass, the mass of the object, times the acceleration due to gravity. So what is the mass of the object? I hope you answered it. That's 5.20 kilograms, as seen in the question, and that's times acceleration due to gravity, which is 9.81 meters per second.
Square.
What does that give us? That gives us 51.01 newtons. Newtons is the unit they use for force. And once again, as we talked about earlier, we're given the distance, 1.55 meters, and now we need to come to the angle. So the angle is the
difference
between the direction of the distance the object moves and the direction at which the force is applied. So here, if you think of what's going on, I'm lifting it this way, and the force is going this way. So both are going up. What does that mean? Well, that means we have an angle of 0. You plug in cosine 0, and you get 1. So the angle is 1 degrees because you do cosine 0. And that now brings us to our next part here. So now we have work equals force. So the force we know is 51.01 newtons times distance, which is 1.55 meters, times, once again, 1 degree. That equals 79.07. Now, how many sig figs do we have? We can only have 3 sig figs, since the original problem, the least amount of sig figs, is 3. So 79.07 is obviously 4 sig figs, so that should just become 79.1 joules. And that is your answer to the first question. Time for question number 2. Determine the work done by the person during the horizontal carrying phase. So this might seem a little complicated at first, but I'm going to explain why it's not complicated at all. The person carries the box horizontally at a distance of 9.70 meters. What's the key word in that question? Horizontally. And you know why that's the key word? Because you know the person is no longer moving the box up and down, but rather left and right on the x kind of axes. And which way is the force moving? Up and down. Force due to gravity is still moving on the object, but you're only moving it horizontally, the object. So therefore, what does that form? It forms a 90-degree angle. Theta then equals 90 degrees. And then cos 90, since you have to do it cos theta, so cos 90, what does that equal? 0. That equals 0. What does that tell us? Then no matter what any of this else is, whatever forces, whatever distances, doesn't matter. It doesn't matter at all in this case, because we already know that cos theta is 0. That the 0 here offsets everything. Therefore, the answer is 0 joules.
The concept of work can be applied to the real-life action of moving a car. As seen in this video, at first the pedestrians cannot move the car and thus no work is done on the car, but eventually they do in fact successfully push the car and therefore in the end, work was done on the car.